okay? I mean, it's a population data. So y is equal to actual value of y is equal to intercept, beta 0 is intercept, plus b1x plus error, okay? So intercept plus slope times x is going to give you value over here. To that, you add or subtract error term, so you have the actual value. Now, what is intercept? Intercept is over here. This is the intercept. Now, so here you can see over here, intercept plus beta 1, which is your advertising, and this is your sales, and x is your, so x is advertising, and beta 1 is slope for advertising, and this is your sales volume. Okay. Now, what you see over here is expected value of y is equal to intercept plus b1 times x. Okay, that's what you're seeing over here. This thing over here is expected value of y. This thing over here is expected value of y. It's not actual y value. Actual y value is this. The expected value of y, you are going to add or subtract error term to come to the actual value. Now, if you spend let's say $10,000 every month on advertising, do you think your sales amount is going to be constant every month? It varies. Okay, it is. They are going to be different numbers. So if you spend $10,000 advertising, your sales might be $1 million, might be 0.9, might be 1.2, might be 0.8 million, things like that. They differ. They are not going to be exactly $1 million per month. They are going to be different numbers. Mean of all those values, if you spend $10,000 on advertising, you expect many different sales values. And the expected value or mean of all those values fall over here. So that's what it is, okay? Now, beta 0 is the y-intercept of the regression line, beta 1 is slope of the regression line, and E of y, expected value of y is the expected value of y for a given value of x. Okay. For each $10,000 advertising you are going to spend, you are going to be having different sales figures. Okay? And this is simply for each value of x, there are many y values, and this is just the expected value of those y values. Y is your sales. Now, here is your population regression line. Okay. Now, what I'm showing you over here is, like when you look at this, data, I mean it's upward sloping, right? So over here, what we are seeing is that as advertising goes up, as X goes up, sales volume goes up. It's upward sloping. Now, you can also see over here, like this is downward sloping. As X goes up, Y goes down. So where do we see this? It is sales and price. As price goes up, sales volume in terms of units is going to go down. In terms of revenue, it might go up, but in terms of units, it's supposed to go down. Okay. Now, so it could be upward sloping or it could be downward sloping, and then you have also this. There is no slope. Doesn't matter what happened to X, Y is not going to change. Okay. Doesn't matter what happened to X, Y is not going to change. There is no relationship. Okay. As far as your sales are concerned, they're all over the place. Now, so I just showed you about population. But population is huge. It is going to take a lot of time. It is going to cost us a lot of money. So instead of using population data, we use sample data. So this is your regression equation using sample data. Now over here, what I did is, I replaced y by y hat. I replaced beta, that beta with a long leg, okay, capital B with a long leg. I replaced it with small b, 0, okay. So this is your sample intercept and this is your sample slope. So we are going to be using sample data to develop our regression relationship. Okay. So here are your population parameter and here is your sample statistic. Okay. Now your sample regression equation is y hat is equal to, that you already saw, y hat is equal to sample intercept plus sample slope times x. X is, let's say, advertising. Okay. Now doesn't matter which method you use to estimate. Your actual value and forecasted value are going to be different. Difference might be very small or difference could be very large. But there is going to be difference. And that is error. Okay? That is called error. Our objective over here is, we want to predict sales. Our objective over here is, we cannot eliminate the error. Error we can only eliminate when you have population data. Our objective over here is to minimize the error. Okay? So that's what we're trying to do over here. We want to minimize error. Okay? Now over here I'm saying, so this is your actual value of Y or actual sales figure, and this is your estimated. Using regression equation, okay, you got this estimated value and this is your actual value. And the difference, and this is the difference. Why I put down a square over here? What's the reason for that? Why I'm minimizing error square or residual square? Why not I simply minimize the sum of the errors?
If we don't square it, they won't all be positive, meaning that some errors will actually cancel out, despite them both being errors.
Thanks a lot, okay? So what will happen over here is, if you don't square, some errors are negative, some errors positive. They will cancel out each other. And what you might end up seeing is that some of those square errors is simply zero. Some of those error squares is simply zero. Okay, now look at this. Just give me an example, okay? So 5, 10, and 50. X bar, let's call it Y bar, is equal to 10. Now, Y minus 1, so this is Y. Y minus Y bar, so it is 5 minus 10 is equal to minus 5, 0, plus 1. When I add them, answer is 0. When I add them, answer is 0. Are you telling me that there are no errors? There are big errors. There are big errors, but the negative errors cancel out positive errors. So that's why you're getting an answer of 0, okay? So we don't sum the errors, we sum squared, okay? Because if we sum the error, answer is just going to be 0. Okay? Now, slope of the estimated regression equation, okay? Over here, this is the formula we are going to be using, and as far as multiple regression is concerned, we are going to be using Excel, okay, to get all these slopes. Now over here, what is xi? Xi is the value for independent variable. This is the mean value of that independent variable. This is your dependent variable. This is the mean value of the dependent variable. Dependent variable is sales, and independent is, let's say, advertising. Okay. Now, as far as your intercept is, small b0 is mean value of y minus b1 x bar. Okay. Reed Auto periodically has a special week-long sale. As part of the advertising campaign, Reed runs one or more television commercials. Just give me a second. As part of the advertising campaign, Reed runs one or more television commercials during the weekend preceding the sale. Data from a sample of 5 previous sales are shown on the next slide. So, number of TV ads, 1, 3, 2, 1, 3. Number of cars sold, 14, 24, 18, 17, and 27. So, when I sum X, all these advertising, I have 10, and divided by 5, the mean value is 2, and same thing, mean value is 20 over here. Now, just by observing it, I can see that as advertising goes up, sales are going up. I can see that, okay? Now, what I'm going to do over here is, I'm going to develop a regression equation, okay? So, sample slope is, these numbers, I'm going to show you the calculation of these numbers. Okay, just 1 second. I have these. So you must be wondering, okay, from where this 20 came, from where this 5 came, from, okay, 4 came, from where this 5 came. I have to show you the numbers now. So here is your X sign, and here is Y. Just copying it down. 1, 3, 2, 1, 3. And then you have 14, 24, 18, 17, and 27. Now then I have X I minus X bar and yi minus y bar. So that is 6. Now, by the way, this is going to be 1, 3, 4, 5, 6, 7, 8, 9, 10. So X bar is 2 and y bar is 20. When I add all these numbers, divided by 5 is 20 and this is 2. Okay? So this is going to be 6. And then you have 4, 0, 6, and 4. How did I get 6? 1 minus 2 is 1. 14 minus 20 is 6. So 1 times 6 is 6. Okay, that's how I got this number. Okay. Now, then I have, so I got this column, and then I have another column, X I minus X bar squared. So let me just draw a line over here, so that you can see the separation. Now, that is 1, 1, 0, 1, 1. How did I do it? From 1, I subtract 2, answer is 1, square root 1. Okay. So I have all this, so add them, and they are 4. And this, when I add it, is 20. So that's how I got these numbers. So these numbers I'm going to put over here. And I have my slope, and I have my intercept. Okay. So here is my regression equation. Y hat is equal to 10 plus 5x. X is TV commercial. Now what's the interpretation of, can you make an interpretation of 10 over here? Can you make an interpretation of 10 over here? In this case, we can. If, let's say you spend nothing on advertising, nothing on commercial, you expect sales to be 10. But what if it is minus 10?
Oh,
Can you say, look, I'm trying to develop a regression equation which will result in least errors. Which will result in least errors. So let me just show you this. And I'm trying to develop a regression line. I'm trying to develop a line which will result in least errors. My question to you is this line a benefit? Is this line a benefit? But most likely this is a benefit. Okay. So this intercept over here, now, let me just do one more. Sorry. Bye. We'll show you another picture. So you just answered me correctly, but now I want to show you another picture. Is this line a benefit? No. Is this line a benefit? They have same slope. They both have same slope. The only thing over here different is intercept. Now, is this line a benefit? The purpose of intercept is just to give a best fit. So over here, like they all have same slope, but because it starts from here, it is not giving you a good fit. This also has same slope. I mean, my figure is not that precise, but let's say they all have same slope. So this is giving you the best fit. So the purpose of, in general, purpose of intercept is to give best fit, okay? Now we can make all kind of interpretation. One of the interpretation is it is the effect of all the variables which are not included in your regression model. Sales don't just depend upon commercials. Sales depend upon many other factors. So that 10 can be the effect of all the other factors which are not in your regression model. But for now, I mean, it's just there to give you better fit. So, what's the interpretation of slope? This is your small b1, sample slope. How do you define it? What it simply means is, if number of commercial increase by 1, your car sales are going to increase by 5. Everything else constant. Everything else constant. If commercials go up by 1, car sales are going to go up by 5. Okay. So you can use it for prediction. So what if next month I'm having 2 commercials? How many car sales I should expect? Okay. So it is, you replace X by 2 and you expect 20 cars. So here I'm just showing you, and you can see this line is a pretty good fit, okay? Now, so over here, I'm introducing another thing, coefficient discrimination. So we draw the line. Like, we drew this line. I mean, by looking at this, it looks like nice fit. It looks like nice fit. Now, but I like to know in terms of numbers, okay, how nice it is. So for that, we are going to be looking at coefficient determination. The sales are not like constant on a straight line. They are changing. They varies. They varies from one period to another period. So what is coefficient determination? It is proportion of total variation in your sales explained by regression relationship with commercials. So if you're looking at the definition of coefficient determination, all those variation in sales, what proportion of those are explained by regression relationship with commercials? SST is the total sum of squares. If you use mean as an estimator, then what is your error? It is just sum of square error, those errors, okay? SSR and SSE, let me just show you by picture over here. You can predict next period sales by sample mean. Just mean, take mean. I mean, you have data for the last 20 months, 24 months, or 50 months. Just take mean and make a prediction. Now, we collected data for the last 24 months, or last 50 months, or last 100 months, and this is data. This is data. I mean, these are all the sales numbers. Okay, so much, and 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 so much. Now, let's say in a particular month, your sales were these, but according to me, your sales are these. So this is error. This error, okay? Now, so here. So this is the error. This is your y minus y bar. This is your y minus y bar. Okay, this is the error you're making. Okay? Now, so here I am putting some more data, some more values. Now what you did is, you developed a regression equation, and this is your regression line. Y. This is your y bar, this is your y bar. If you use mean as an estimate, mean is over here, actual value is over there. Mean is over here, actual value is over here. So your error is y minus y bar. Can you see that? But on the other hand, if I use my regression line to give me estimate, my estimate is going to be over here. My estimate is going to be over here. How much is the error then? Actual value is this, estimated value is this. Error has gone down substantially. Okay. Error has gone down substantially, okay, over here. So this is so this thing is y hat minus y bar. Your error has gone down by this much. how much error is still remaining? How much error is still remaining? It is y minus y hat. Can you see that? So I have a choice. I have a choice. I can use mean as an estimate, and I use mean as an estimate, and suppose the actual value is this. Actual value is this. So if I use mean as an estimate, my error is going to be from here to here. Big error. But if instead of that, I use regression line, then according to regression line, my estimate is going to be over here. So which means my error is going to go down by this much. So this is the error which will be remaining. Error has gone down substantially. Okay. Now, I'm just not looking at one point. I'm looking at a lot of points. So if I add these errors, what would be the answer? Y minus y hat. You have all these y values. From those you subtract y hat value. What's the answer? Answer is going to be 0. Y minus y bar. You have all these values, and from that you subtract mean value and add them. What's the answer? Answer is 0. 0 doesn't mean that there are no errors. There are errors, but negative and positive, they are cancelling out each other. So what I'm going to do over here is, I'm going to do some more calculation. Okay? So here is, I have another column. Let's call it SST. And SST is simply yi minus y bar squared. So using my diagram, from each value, I'm going to subtract mean value and square it. So I'm doing that, and the answer is 25, and then 25, and 0, and 25, and 25. Total is 100. I'm calculating another column, SSR. And what is SSR? SSR is y hat minus y bar squared. Y hat minus y bar squared. This is the reduction in error if instead of mean use regression equation. So y hat minus y bar. Now I need one more time. So here is y hat. Your regression equation is this is your regression equation. If I replace 1 with x by 1, answer is 20. If I replace x by 2, answer is 25. If I replace x by 1, answer is 15. If I replace x by 2, answer is 20. If I replace x by 3, answer is 25. Okay? So that's what I'm doing over here. So replacing x by 1, answer is 15. And this is going to be 25, and this is going to be 20, this is going to be 15, and this is going to be 25. So I have my y hat values. So now what I'm doing over here is, from each y value, I am going to be subtracting y hat from 14 minus 15, 24 minus 25, 18 minus 20, 17 minus 15, 27 minus 25. That's what I'm doing now. Okay. And I'm also going to do like this column, from each y hat value, I'm going to be subtracting the mean value. So let's do that first, okay? So SSR, y hat minus y bar square. So from 15, I am subtracting 20. So that is 5. The square is 25. From 25, I am subtracting 20. The square is 27. You know what? I think these numbers are wrong, right? Yeah. I changed the switch the columns. Thank you guys, you're so nice. Okay, that you don't say anything. This is 36, 16, 4, 9, and 49. (14) minus 20 is 6, negative 6. Square it is 36. 24 minus 20 is 4, square it 16. So now, so these numbers should actually come over here, okay? So 0, 25, and 25. So this is 100. How did I get this? 15 minus 20 is 5, square it 25. 25 minus 20 is 5, square it 25. So that's how I got it. And then the last one is yi minus y hat square. Now over here, yi is this. So 14 minus 15, square it. So that is your SSE. 14 minus 15 square it, so that is 1. 24 minus 25 square it is 1. 18 minus 20 square it is 4. 17 minus 15 square it is 4. 27 minus 25 square it is 4. And over here you have 40. Let's just look at this. Y minus y bar. If you use mean as an estimate, then your error is from here to here. Y minus y bar is error from here to here. But if you replace mean with regression with y hat, then your error is going to go down by so much. And this thing is y hat minus y bar, the reduction. And this is the error which is remaining, which is y minus y hat. Now, look at this chart over here. SST is total sum of the square error. If you just add the error, the answer is going to be 0. So we square it. Okay. SST is total sum of the square error. SSR is sum of the square regression. SSE is sum of the square error. When you are using mean as an estimator, then this is going to be your total error square. Okay. This is the reduction in your error, and this is the error which is to remain. You are not able to eliminate all the errors, but you are able to eliminate quite a lot. You are able to reduce your error quite a lot. This is still this. Now, so SST is 140 is equal to SSR plus SSE. So 100 plus 40. This is the total error which we split it into error which we are able to explain or error we are able to eliminate, and this error is still remaining. Now remember, we are doing it in squares, okay? Because if you don't square it, answer is just going to be 0. . Now, when I take a ratio of SSR over SST, of the total error is 114, total error square 114, and this one was able to eliminate, explain. So when I take 100 over 114, the answer is 87.72%. Now what's the interpretation of this? The regression relationship is very strong. 87.72% of the variability in the number of cars sold can be explained by the linear relationship between the number of TV ads and the number of cars sold. So the interpretation is 87.72% of the variation in car sales is explained by the regression relationship with TV commercials. Can you tell me what could be the maximum value of R square?
100.
100, okay? Thanks a lot, okay. This is your total sum of square error. Maximum value of R square is how much? 100%, okay? That's the maximum. If you are able to explain all the errors perfectly, then there is no error left. So for example, look at this. So here is your data. You collect the data on sales, and here is mean. Here is mean. And here is your regression line. Total error is this minus this, this minus this, this minus this, this minus this. But when I look at my regression line, if I use regression line, there is no error left. I'm able to eliminate it perfectly. This thing will be equal to that. So this is what happened, okay? If your line is perfectly okay, I mean all the points are falling on exactly on the line, there is going to be no error. In that case, your SSR and SST both are equal. So 100%. Okay. Now, what's the minimum? That is your y bar. Now, what's the slope over here? Can you tell me what's the slope over here? There is no slope. So, this is your y bar and there is no slope. Slope is 0. So, this is also, let's say, your y hat. Y hat is going to be simply y bar. So in this way, in this case, I mean, you are not eliminating any error. This thing, y I minus y hat, is going to be equal to this, is going to be equal to that. Which means error you are able to explain is nothing, 0. Error unexplained are going to be 100%. So this is using Excel. I'm going to show it to you later on, okay, how we do it using Excel. We are going to be looking at the output. Now, as far as coefficient determination is concerned, it tells you the strength of relationship. And it goes from 0 to 100%. It goes from 0 to 100%. 0 is no relationship and 100% is perfect. Okay, all the errors in your, all the variation in your sales volume, you were able to explain by having a relationship with TV commercials. So it goes from 0 to 100. There is another measure which is coefficient of correlation. Not only it tells you the strength of relationship, but it also tells you the direction of relationship. Can coefficient determination be negative? Can coefficient determination can be negative?
Yes.
Coefficient determination.
Oh wait, no, that one.
How can it be negative when you're squaring all the values?
I've heard it.
It's not going to be negative. It is always going to be positive. So it doesn't tell you, it tells you the strength of relationship, how strong two variables are related to each other. Okay, but it doesn't tell you the strength of relationship. Sorry, it doesn't tell you the direction of relationship. For that, you have coefficient of correlation. Not only it tells you how strong the relationship is, but it also tells you the direction of relationship. It could be negative, it could be positive. It could be negative, it could be positive. Now, so here is, this is your coefficient of determination. A square root of that is coefficient of correlation, and to that you just include sign for your slope. If your slope is negative, you put negative. If your slope is positive, you put positive. So coefficient determination, coefficient of correlation is simply the square root of coefficient of correlation and the sign. Or I can also say coefficient determination is just the squared value of coefficient of correlation. Now, so here is your coefficient of correlation. Find out the square root of coefficient of determination, and to that you include the sign, and the answer is 0.9366. Can you tell me what could be the maximum value of coefficient of correlation? What could be the maximum value? What could be the maximum value? 1. Absolute 1, okay? Plus 1, minus 1. Let's say this is your data. All the values are falling on regression line. Exactly. There is no variation left out. So coefficient of correlation over here is over here. Negative. Perfect negative relationship. Over here. Less than perfect, but still pretty strong. Less than perfect, it's strong, it's still close to it. I mean, the maximum value of coefficient of correlation is 1, absolute value 1. Okay. So this is close to 1, right? No relationship. When you are making portfolio, let's say 2 securities, you want to put 2 assets in the portfolio, the relationship between those 2 should be what? Should that portfolio be RBC and CIBC? You want to make a portfolio of 2 stocks. Should it be RBC and CIBC?
Depends on the goal of the portfolio.
RBC and CIBC. Very
Are
clear.
we trying to minimize risk or are we trying to maximize return? Because depending on which they're very different
Okay.
plans.
RBC and CIBC. Okay.
Very risky.
Is there any benefit of having a portfolio consisting of RBC and CIBC?
Nah.
I mean, look at the bank's results. I was shocked. TD, $4.25 billion. My God, quarterly result. Doesn't matter which bank you look at. Billions and billions of dollars they are making. Is there any benefit of having these 2 assets? Answer is no. If CIBC is doing good, RBC is also doing good. What we are looking over here in portfolio is if one asset is performing poor, other asset is doing much better, that it can even take care of poor performance of the asset which is doing bad. So ideally, we like to have assets which are highly negatively correlated. Can you tell me if between 2 assets the coefficient correlation is -1? If between 2 assets the coefficient of correlation is -1, what could be the minimum standard deviation of that portfolio? Two assets perfectly negatively correlated. Okay. What could be the minimum standard deviation for that portfolio? The standard deviation is measured total risk.
Would it be 0? Because they are
Confident. 0. Answer is 0. You can have infinite portfolios, but there is going to be one portfolio of those 2 assets which will result in 0 standard deviation, which means risk-free. Okay? Now, of course, okay, it is not, it's difficult to find, okay? So you should be looking at assets which are negatively correlated, or at least the assets which don't have high positive correlation. Okay? Because there is no point of having assets which have high positive correlation. There is no need. I mean, just extra work. Okay, why you should be putting CIBC and RBC? Just put one. Assumption about the error term. The error is a random variable with a mean of 0. Now, the difference between actual value and the estimated value is error. So we are saying over here is just a random variable. Now tell me, when we add the errors, I'm not talking about squared value. When we add the error, what's the answer? When you just add the errors, when you just add y minus y hat, when you just add y minus y bar, what's the answer? Answer is 0, guys. That's why we are squaring. Okay. Answer is 0. So the error is a random variable with a mean of 0. One error doesn't depend on another error. That's what we are saying. The variance of error denoted by sigma square is the same for all values of the independent variable. So actually, this is what we are saying. Here is x, here is error, and this is 0. These are all errors. I mean, do you see any pattern over here in errors? Do you see they're going up, going down? I mean, non-linear relationship going like this, going like that. What I see over here is there is no relationship. One doesn't depend on the other. They're just random. Each x value has many y values, and the difference between those y values and your y hat is an error. So these are, let's say, if x is over here, these are the errors. If x is over here, these are the errors. So the mean of those errors is just 0. And as far as dispersion is concerned, it seems to me that it's just the same. Look at this. Do you see any relationship, any pattern? Something like that. Do you see any pattern? I see. Your error is increasing. As your x goes up, your error is increasing. These are systematic things, okay? So there is some deficiency in your model. You have to fix it. It should be less random. Now, other assumption is the error is normally distributed random variable. Now, let's just go back to you took a sample data and you found sample regression equation y hat is equal to 10 plus 5x. Is there any relationship between your TV commercials and sales? Is there any relationship? Is there a relationship, do you see any relationship in your sample data between TV commercials and sales? It's obvious. Your slope is 5. Thanks a lot, okay? Your slope is 5. As TV commercials goes up, sales are going up. There is a relationship. If this is 0, that means there is no relationship. If this is negative 5, that means sales go down. As x goes up, sales go down. Over here, as x goes up, sales go up. There is a relationship. Relationship is if your slope is not equal to 0. Okay. So it's not equal to 0. Can I say, I just took a sample data, can I say that in my population also there is no relationship? Now look at this picture over here. This is your population data. Do you see any relationship over here? You don't see anything. Just as a coincidence, I collected data and this is my sample. Do you see a relationship? My eyes are running, my throat is hurting, it's allergies. I can't spend time outside. Grass, everything. So over here, you see relationship. But when you look at the whole population, there is no relationship. So what we are going to do over here now is we are going to do hypothesis testing and confidence interval estimation to determine if in our population also there is a relationship. Testing for significance. To test for a significant regression relationship, we must conduct a hypothesis test to determine whether the value of beta 1 is 0. Remember that a small b is sample slope. This beta is population slope, okay? So we found that in our sample data, there is a relationship between commercials and car sales. Is there a relationship in our population also? And the relationship means that the beta is not equal to 0. We can use two tests. One is t-test and the other one is f-test. We can use either one of them, okay, to determine whether there is a relationship or not. Now, testing for significance. An estimate of variance. The mean square error provides the estimate of variance, and the notation S square is used. Now, can you tell me what this y minus y bar square is? What is y minus y bar square is? It is sum of square errors around mean. See? Y minus y bar. Y bar is mean. From each y value, you are subtracting mean value. And then squaring. What is this yi minus y hat square?
It's the sum of the errors around the regression.
Around the regression line. It is sum of square error around regression line. You like this to be high or less? More or less? What do you want? More? You want this to be more or you want this to be less? You want it to be less. As little as possible. Tell me. What is this thing over here? Is there any dispersion around the regression line? So this is 0. What is over here? There is a lot of dispersion around regression line. Regression line is just useless. So this is being a very large number. Now, so over here, mean square error is just like a variance. Is a measure of dispersion around regression relationship. If you find a square root of that, that is just like a standard deviation. Okay, a standard deviation of dispersion around regression relationship. Okay? SSE is equal to yi minus y hat square, and what is that? Look, what's the formula to calculate y hat? It is intercept minus b1 x1. Okay, so that is your formula square. Okay, you guys are okay? Now why this is minus? Because it's open brackets. Okay, if it is closed bracket, then I would have put plus over here. Now, do you remember from yesterday? What I can now say, right? So this is just something similar, okay? Like if you recall from yesterday, I mean, you had, if you want to estimate, let's say, z is equal to x bar minus mu over, this was the case, okay? Now over here, this is your variance, S is equal to MSE equal SSE divided by n minus 2. Now why there is 2 over here? S is standard deviation, and when I find a square root of that, sorry, S is standard deviation, when I find a square root of MSE, I get S. Now MSE is just like variance. How do you get that variance? It is S is sum square error around regression relationship divided by n minus 2. Why there is 2 over here?
Is it because it's two portfolios, so you need to take into account 2 degrees of freedom, or?
So we can say that 2 portfolios, yes, so there are 2 variables. So there are 2 variables, so that's an indicator of 2 variables. I can now say these are the number of unknowns or the things which I am estimating. So you are estimating an intercept, you are estimating a slope. You don't know population intercept, you don't know population slope, so that's why you have n minus 2. So this is going to give you a standard deviation around regression line, okay? Now, my hypothesis statement is going to be B1 is equal to 0 and B1 is not equal to 0. If it is 0, there is no relationship. If it is not 0, there is a relationship. I don't have to have 0 over here. I can also have an assumption that population slope is equal to less than 4. It is less than or equal to 4. It is more than or equal to 4. I can have those. I can test for anything. Here I am only interested in whether 0 or not. Now, as far as statistic is concerned, it is being sample slope divided by standard deviation of sample slope. Now, SB1 is equal to standard deviation. Which standard deviation I am talking about? I am talking about this standard deviation. I am talking about this standard deviation, which is measure of dispersion around regression line. So that divided by xi minus x bar square, okay, square root of that. Now, SSE, so if you like to find out S, can you tell me, we did the calculation earlier, right? And S is equal to MSE, which is like variance. That is equal to SSE over n minus 2. Can you tell me how much is your SSE? Do you have it anywhere? Have you seen it anywhere? How much was that? 14. So it was y minus y hat, and you square each of that value, so that is 14. N minus 2, there are 5 variables. Sorry, there are 5 observations, 5 minus 2, okay? So that is your denominator, n minus 2, okay? So this is going to give you 2.60. So if you are interested, okay, you can put that number over here, 2.60. Now, over here I have xi minus x bar square root of that, okay. How much is xi minus x bar square? Do you remember? 4, okay. So this is going to be 2, right? So that is 1.08. Over here, I am dealing with the distribution of B1. It has a mean equal to, so there are a lot of B1s. Lot of small, this is small B1, okay, the sample slopes. So I'm dealing with the distribution of sample slope, which is mean equal to population slope. And it is standard deviation equal to SB1. Just like what you did earlier. Okay. Here I was dealing with sample mean, so this is standard deviation of sample mean. Here I'm dealing with sample slope, and this is standard deviation of sample slope. Now, so we are using T statistic over here. Okay. It is B1 divided by SB1. Why I don't have? Remember T is equal to like Z is equal to X bar minus mu over standard error. So why don't I put over there this B1 thing, beta 1? The reason I'm not putting it over there because I'm assuming it to be 0. But if this number, if I'm not testing for 0, I'm testing for 4. I'm saying population slope is 4. I'm saying population slope is at least 4 or not more than 4. Then I have to put over here a small b1 minus 4 or population slope. So you can do the testing for relationship, but you can also do testing for any particular slope. So over here, I'm going to solve it. Now, reject ratio if p value is less than or equal to alpha, or t value is less than or equal to t alpha over 2, or t alpha over greater than or equal to t alpha over 2. T value is based on t distribution within n minus 1, 2 degrees of freedom. 2 degrees of freedom are what? The number of estimators you are having. So you have 2 estimates. One is intercept and the slope, so that's why you have 2. Or we can also say you have 2 variables. In a regression model, if you have 10 variables, this will become n minus 10. Okay. So hypothesis testing, the very first thing you do is you state your hypothesis statement. B1 is equal to 0, beta 1 equal to 0, beta 1 is not equal to 0. You specify the level of significance, so that is 0.05. Select the test statistic, we are using T, and so that is sample slope divided by standard deviation of sample slope. Now, there are 3 degrees of freedom, and alpha is 0.05. So what is the T value? I'm going to take a break in just 2 minutes. So 3 degrees of freedom. Now, before I go into that, can you tell me, is it a two-tail test or one-tail test? It's a two-tail test. I don't care if it is less than 0 or more than 0. Doesn't matter. I like to find out if it is 0 or not 0. It's a two-tail test. Alpha is 0.05, that means half of the alpha is in the lower tail, half in the upper tail. So you should be looking under 0.05. So 0.05, 3 degrees of freedom is 3.182. So it is plus minus 3.182. So we found our critical value. is your T distribution. And then you are going to be finding out our T observed, okay, which is 4.63. So 4.63 is over here. Rejected. Now, what is the P value? Three degrees of freedom. Try to locate 4.63. Can you see over here is 4.541? And here you have 0.01. But mine is 4.63, which means should be less than 0.01. Even if I take 0.01, 0.01 times 2, because the two-tailed test is going to 0.02. Your p-value is less than alpha. Remember from yesterday, we spent a lot of time on p-value. If p-value is less than alpha, reject it. And that's what we are doing over here. Your T observed is in the outside region, it's in the rejection region, this accept. Is rejected. So T value is in the rejection region, reject ratio, P value is less than 0.02, which is less than alpha, reject ratio. You guys are okay? So let's take a break. Now, we'll start the class at 10 minutes, okay? Okay, so let's start. So for sure we'll start at I think you guys are tired. 10, 15?